Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Welcome to this Australian Water School webinar brought to you by iSwarm. Thank you for joining us today to discuss advancing groundwater-dependent ecosystem detection using radar. It'll be presented by Dr. Tanya, Principal Research Scientist at CSIRO. It's great to have you all here, and it's really good to be here myself, Trevor Pillar, National Partnerships Manager here at iSwarm and the chair of the webinar. But it's about you guys. Well, certainly there's a lot of people here. Thank you for joining us, and thank you also particularly for joining us 30 minutes early. We realised we brought this early by 30 minutes, but it hasn't affected the numbers I can see. And look at the spread of participants out there in the Pacific, right across to North America and up north, one in Mongolia. Amazing. Thank you so much for joining us. Well, you can see there's a fair bit of training, webinars, online courses coming up in the next 2 months, and pretty much most months actually from iSwarm. This is the state of play, and we really enjoy doing it, and a great crowd of people come along. We encourage you to go on the website and look up the details. Dr. Tanya from CSIRO, Principal Research Scientist, specialising in plant physiology and water relations. Hi, Tanya. Thank you. Wonderful to see you here today. I'll keep going with your little intro. I won't do the whole thing, but specialising in plant physiology and water relations in floodplain and forest management. Tanya's with the CSIRO in 1993, undertaking research focused on groundwater-dependent ecosystems in Australia and Nepal. So this is going to be some discussion, I would say, and of course at the end there, water balance projects with the Murray-Darling Basin. Done a fair bit of work, Tanya. Where are you based?
I'm based in Adelaide at CSIRO.
Oh, right. Lovely. South Australia. Lovely South Australia. That's fantastic.
Yep, sunny today.
Yeah, that's a good thing. We need more rain, but it's nice to have sun. I have a burning question. That is, what is your motivation and driver as you come to this topic? Well, I suppose more than just this topic.
Yeah, so I grew up in a riverine region, and so I have this passion to ensure that we can nationally and globally provide ways that we can protect our watery ecosystems in our future of ever-growing water scarcity.
So when you live in that and grow up in it, you get it in your blood, really, I guess.
You certainly do. And
I've picked that up. I do pick that up.
Yes, I've been fortunate enough to go back to the regions that I grew up to do some of this work as well.
Fantastic. No, that's really, really good. Look, we won't waste too much more time.
That sounds good, Trevor. Thank you.
All right. I'm completely over to you. Look forward to it.
Okay. Just remove Trevor from my screen. There we go. So hello, everyone, and thank you for coming along. As Trevor's alluded to, today we're going to talk about groundwater-dependent ecosystems, or we refer to these as GDEs. But first, I'd like to highlight a webinar given in this series in October 2018 by Ben Di Gregorio, talking about Australia's GDE Atlas, and this is in relation to groundwater management and decision making. If you haven't seen it, take a look, as this is a great webinar, and we are referring it to today. Acknowledge my co-authors to this presentation, and also make it really clear that it's actually Pascal who has led the radar GDE development method, and he's been supported in different ways by Luke and myself, but also Jodie Pritchard has contributed to some of the information to this PowerPoint. So let's get started. What are groundwater-dependent ecosystems? So these are, and I'm going to read from the screen, but these are natural ecosystems that require access to groundwater to meet all or some of their water requirements on a permanent or intermittent basis. And this is so that they can maintain their communities of plants and animals and ecological processes and functions in terms of ecosystem services. Now, this definition has been developed in Australia, and I think it's been a country to some extent that has led the way into GDE research and understanding in the past, and we still continue to in the future. So what are GDEs? Well, again, in Australia, we've turned these into different types, and so we call some of these the ecosystems that are dependent on a surface water expression of groundwater, and these include estuarine and nearshore marine ecosystems. They're wetlands, they're lakes, seeps and springs, also river base flow, so that's the base flow in a really dry period where water might remain, is generally groundwater fed, and also terrestrial fauna. But there's also ecosystems dependent on subsurface expression of groundwater, and this includes terrestrial vegetation, and often you might see in the literature we refer to these as GDEs, or groundwater-dependent vegetation. And then, of course, we also have aquifer and cave ecosystems such as stygofauna and troglofauna. And so, as you'll see, some of the photos I've shown today are trying to demonstrate different types of groundwater-dependent ecosystems or groundwater-dependent vegetation. Groundwater dependency, what is it? It means that in arid and semi-arid locations such as Australia and other locations around the world, plants and animals will evolve to use groundwater to support their continued existence and their reproductive cycles. So as you might expect, this is often at the end of dry or extended periods when water is becoming scarce and intermittent streams become disconnected pools of groundwater that is groundwater fed water, I guess. And this provides refugia, especially to animals, hence animals are groundwater dependent. And we know from field studies in the Murray-Darling Basin, for example, that floodplain trees can switch between multiple water sources, and this includes groundwater, even when saline, to supplement their water requirements, ensure that they continue to at least maintain some leaf canopy and life. Studies have also identified that GDEs exist in wet tropical regions, and often access to groundwater is during the dry season before the monsoon season begins. What are the consequences of change in groundwater availability? So this can lead to, in the aspect of trees, which is a very visual assessment, decline in health. For other systems, it's decline in recruitment or aerial extent. Ecosystem structure can be altered, and worst case scenarios, you can lead to entire ecosystem collapse. GDE condition is also compromised by surface water diversion, land use change, weed infestation, and pollution and disease. And so one of these examples is this photo in the top corner here, where these trees have declined in health due to reduced base flow in river systems. And what this photo is showing, that the trees have declined and it's actually required an artificial environmental flow to restore some of that canopy you see there. So faunal decline can also occur, and this is due to reductions in groundwater expressed as surface water, often in relation to over-extraction. So increases in groundwater availability to ecosystems can also be harmful, particularly if intermittent access changes to root submersion for trees, for example. So as groundwater level rises, or as a stream that was once intermittent becomes permanent, in relation to things like groundwater dewatering associated with deep earth exploration, this can have a negative effect on groundwater-dependent ecosystems or vegetation. So other industries that might be related to this over-extraction include irrigated agriculture, could be drought, mining, human consumption, plantation, forestry water use. So today we're going to talk primarily about GDEs, or groundwater-dependent vegetation. And these can include riparian vegetation that rely on groundwater provided by river base flow, springs, wetlands and lakes, but also terrestrial vegetation. So this is vegetation that might be at a distance from a river, say 100 metres, and generally might have some surface flow to sustain them, but much of the time are dry land and will rely on direct access to groundwater. And there are many methods in order to identify GDEs and GDEs. So I've provided the link to a new document called the GDE Explanatory Note, and that will give a nice overview of some of these methods. And some of these include remote sensing, in-field water balance studies, isotope analysis, and so on. However, identification alone it really isn't sufficient, and regular monitoring is also required. However, the issue around GDEs and monitoring is generally scale and the cost of monitoring. So we're always looking for new ways to provide cost-effective and broad-scale methods to help understand where groundwater-dependent ecosystems are, or vegetation, but also to understand how they might be changing over the long term. Ideally, as time goes by and we increase our research efforts, we'd also like to understand when trees are connecting with groundwater and how much groundwater they're accessing. At this point, there's a few studies in the remote sensing realm that have looked at this, but it's actually a much harder area of groundwater-dependent ecosystem study to try and understand. So our intent here is to provide, I guess, a more cost-effective way to monitor in the first instance. Now, before I launch into the remote sensing component, I want to be clear in saying that I'm leaving out a lot of the technical detail around remote sensing and also the actual method that we developed. And this is really due to the fact that we have a very varied audience, and this is an assumption that I am making, and that audience is likely to consist of perhaps remote sensing experts through to on-ground practitioners that may not understand the complexity involved. And as we've seen, a lot of the audience that is here is related to government and policy. So what I am keen to convey is that we have developed a new method to advance monitoring of GDEs and to demonstrate the benefit that this method provides over contemporary remote sensing methods that have been trialled in the past. So today we'll talk about optical remote sensing, and I'll overview that here. And when I talk about optical, I'm talking about MODIS and Landsat, and I'll give a little bit more detail on that in the next slide. But basically, optical methods provide broad-scale assessment. They can be cost-effective as well, and they can allow us to understand temporal change. However, the issues associated with optical remote sensing are cloud is a problem. And you can see I've highlighted an area here in red, and those black squiggles are showing, sorry, the white squiggles there, sorry, are showing some cloud, and that obscures our total view of the landscape. Satellite frequency is also around 14 days, which is not too bad a temporal resolution, but we're also working at a pixel size of 25 to 30 metres at best, and we refer to this as spatial resolution. And we also have some issues with shadow, and that depends on when the satellite's passing overhead and the shadow time of day that trees, for example, or buildings might cast. So that again obscures the view of what's happening on the ground. So again, you know, we need new methods to advance the ability to accurately monitor at broad scales. So optical remote sensing, such as Landsat and MODIS, use visible wave bands, so images are similar to how the eyes see the world. So today I'm using an example comparing the two types of remote sensing, and this was undertaken at Angkor Wat in Cambodia. And as you can see, the optical image on the left looks similar to a photograph. Radar, however, emits a wavelength as a microwave, and this is reflected back to the satellite. What is emitted back to the satellite is land surface roughness, which allows us to understand what the surface type may be. And so if you look at the radar image on the right there, note that it's at a much broader scale than the Angkor Wat image, but basically this rectangle here is being shown as this little feature here. But it shows a lot, very different detail around that. What this is actually a moat. So there's very different detail being shown around this moat. And so the radar itself is not influenced by weather nor cloud, but it provides a better definition of the land surface. So in the radar image above, the pink is sea and reap, so that's demonstrating buildings, township. Green is forest, land cover. Roads and water bodies are black, and fields are purple. And whilst we can kind of see some of this in the optical image, the surface roughness and the radar image provides certain benefits. that can help enhance what we're already understanding about GDEs. The most important thing being that radar is not influenced by weather and cloud. So the method that we developed today uses synthetic aperture radar, or this is referred to as SAR, S-A-R. So from 2014 to 2016, we saw the introduction of global SAR satellite acquisition. So Sentinel-1 was launched in 2014, and this was followed by a twin satellite called Sentinel-1B in 2016. So as I've already said, SAR emits electromagnetic wavelengths, and these are in a range of 3 to 24 centimetres, which are wavelengths not visible to the eye. So short pulses of energy are sent towards the ground at a known angle, and the pulses bounce off the surface targets, which might be buildings, grass, trees, roads, and energy is reflected back to the satellite antenna, and this is referred to as backscatter. And so that's what this image here in the white is demonstrating, those different angles of backscatter that have reflected back, hopefully, to the satellite. More energy the target backscatters, the brighter the land surface target will be, and we can see that in this bottom corner here where we're showing a SAR image example. So recent studies have shown that the longer wavelength penetrate deeper into vegetation, canopy and soil, indicating the benefits for future monitoring, not just in terms of groundwater-dependent ecosystems, but vegetation and other areas of hydrology, ecology, geology into the future. So we're still in early days, I think, of SAR imagery. So to expand on this backscatter a little bit more, this image is showing the different surface features that exhibit different scattering characteristics. Urban areas, for example, have very strong backscatter. Forest has an intermediate backscatter, and calm water, which is a smooth surface, has a low backscatter. So from the data that's received back, we can understand that the land surface and the return angle will help us to identify what sort of surface we're looking at depending on roughness. And then we can correlate the data to the type of surface it might be. For example, vegetation surfaces such as trees are rough and will return different angles and penetration depths depending on the band. And we can see that demonstrated here in this image. So SAR is collected in a number of different bands within the 3 to 24 centimetre bandwidth, and are given letters to represent each band. And I show a couple of these here, so X band, C band, L band. But in this study, we're using the C band as is suitable and freely available to researchers or end users around the world. And C band is collected in a 4 to 8 centimetre frequency range. There is, however, a lot more complexity to the method that we've developed, but I think this is best read in our journal paper, which is available at the link shown in the PowerPoint. And so you can go back to this recording and grab that link and read that paper for further of that technical detail. So why SAR? As I said, I think the biggest advantage from my years of expertise in GDEs is there is no missing data due to clouds. So this has a significant benefit in tropical areas, and in Australia, that's Northern Australia, and cloud-dominant areas such as Tasmania. It also has a slightly better satellite return visit, so Landsat's around 14 days, SAR is 12 days, bearing in mind that it is actually every 12 days because we will have no missing data related to cloud. But there can also be this improved spatial resolution of 5 to 10 metres, which we can refer to as a pixel, but it's a different analysis method. And representing in a 5 to 10 metre pixel is related to the way the data is analysed. So I guess in synthesis, what I'm saying there is we have better spatial resolution to understand what's happening on the ground surface. So what's our hypothesis for why we're using radar to identify groundwater-dependent vegetation? Well, GDEs are structurally stable in time, so the leaves and the branches, because they're accessing water through the driest months. Hence, the biomass of the canopy is stable rather than declining due to water stress. So what we're saying is that when it's dry, the trees are continuing to thrive because they have this access to groundwater, whereas neighbouring vegetation, which may not access groundwater for a variety of reasons, will decline in their canopy extent as a result. So we use a similar theory actually when we're using Landsat methods or other remote sensing methods, but it's just a different approach using radar for the reasons I've detailed as in the dot points above. And what we've actually done is reported what we call a SAR GDE index. So like I said, more technicality behind this method than I'm going to present, but what I will talk about is an index that we've developed to make it easy to understand what it is we're trying to demonstrate. So our study locations. What we wanted to do was to find 2 different study locations in Australia, one that was more tropical and one that was more temperate. So both of these regions, we've picked one in the Wildman-Kakadu region in Northern Territory and a second one in the Penola region in the southeast of South Australia. So both of these regions are subject to quite significant cloud over time, but also we wanted to develop a method that works in these very different climatic zones. And so I think another thing to emphasize here is what we're presenting today is a really simple approach, and it has no calibration or optimization, and I'll talk about that at the end a little bit more. So you can see we've identified the small regions we're working in using those yellow boxes, and so my next step is to talk about the results that we've seen as a result of undertaking this radar remote sensing and developing this method. So in the top row here, we have the entire scene of the SAR imagery that we were using. And in the second row, we're zooming into a specific point. So what we've done in order to validate the results from the SAR method is to look at the polygons within the Groundwater-dependent Atlas of Australia, so the GDE Atlas that I referred to earlier. So there's some polygons in there which are known as known GDEs, and these have been identified using field-based research, and we've used them for comparison to determine how well the SAR imagery is representing GDEs. So that's been our validation. So in the left-hand side there, we're showing the South Australian region and also the Northern Territory region. And you can see in that zoomed in area how the SAR GDE index is demonstrating that anything really above 10 is likely to be a GDE, and when it's getting up into this red area, it's very, very highly likely to be a GDE. And so you can see we have a lot of yellow, orange and red falling within those polygons that have come from the GDE Atlas. What I will emphasise is there will be some areas of red in the South Australian imagery that actually are representing plantation forestry, and those areas were not provided as polygons in the GDE Atlas. So this isn't actually an error in determination of GDEs in our method. It's actually that these areas are not represented in the GDE Atlas at this point in time. And then we've zoomed in further again, just to have a bit of an understanding of how well are we comparing with the GDE Atlas. And this is bearing in mind we have no optimization or calibration of the approach. So SAR data is in the second row of images, and then the GDE Atlas polygons that are these known GDEs are provided in the top row. And what we find is in South Australia, we have an 89% similarity with those GDE Atlas polygons that appear, and a 91% similarity in the Northern Territory. But what I'll also emphasise here too is that the GDE Atlas information, and I'm referring to the polygon size, is often limited by the vegetation mapping and the size of the polygons used. And while this has been improved over the last several years, we think the SAR method is giving a finer detailed representation of where GDEs are in and outside of the map polygon regions. So instead of getting a blanket, there's just GDEs in this polygon, the second image is showing a more, in a way, speckled representation of where GDEs are, identifying that, they may not be present in all of that polygon. And in actual fact, there are some that are probably present outside that polygon, but we just haven't known about them or had the field validation to support that in the past. What I'll also emphasise here is that the method actually identifies water well, as you can see here by the blue areas. So I guess to reiterate from our results here, and this is zoomed in again, we are finding that there is an 89 to 91% match between the SAR representation of groundwater-dependent vegetation and those known those GDEs from the GDE Atlas. So I think this is demonstrating a really promising approach that we can take in the future. And before I say any more, I'll go to the next screen before I steal my own thunder. And it's providing a useful way to map groundwater-dependent vegetation across very, very broad scales. So we can look at this at the much smaller scale, but this method, as you can see, those regions were quite large that we've identified GDEs using SAR with. So with more research to ensure we're showing the right information in the future, we should be able to start rolling this method out across all of Australia, essentially. So in summary again, we're showing a 90% similarity, and I'll emphasise that this is using a simple approach with no calibration or optimisation at this stage. So SAR also brings, this broad scale monitoring capability to other methods such as those used in the GDE Atlas. But this is bringing a capability at least annually. So in the GDE Atlas, when we use the Landsat, we identify GDEs using 10 years, an average of 10 years of Landsat data, whereas this is providing an approach that can be undertaken annually. What I'd also like to stress at this point, though, is that no one method on its own tells the entire story about groundwater-dependent ecosystems. And I'd like to emphasise that the multiple lines of evidence approach is the preferred way to map and monitor GDEs. So this is an approach that we took in the GDE Atlas, and I've added a link to this slide to the publication that talks about the multiple lines of evidence that we've used, and that other agencies are also taking to understand where GDEs are located. My PhD students, which I'll talk about in a minute, will incorporate this multiple lines of evidence approach into their research in the current research that they'll be undertaking. So the next steps, we need to test the method against local data, and I'm in early stages of discussion with some scientists in WA to use this 20 years of data for Nangara Mound in Western Australia, because what I forgot to say is at the moment we have a warehouse of 4 years of SAR data, so we can start to go back and look at temporal changes. We want to optimise the index so that we can assess the value of increasing the complexity of the index for better accuracy, and also incorporating multi-wavelength imagery such as NovaSAR. So what I'm conveying here is that bringing in more complexity may actually not be beneficial to what we've already developed, but we actually need to identify that. We want to investigate this benefit of temporal change analysis in relation to groundwater depth change, and combine the results with other methods to understand how much and when groundwater vegetation use groundwater. So back to PhD students, because this is currently, for me, I guess the most rewarding way to start advancing on this method. So we currently have one PhD student, and he's working on statistical optimization and automation of the index that I've presented today. followed by an investigation of temporal change to understand seasonal changes in this vegetation stability over the last 3 to 4 years of SAR data acquisition. So we want to start looking for thresholds in changes to that SAR GDE index that might help us understand at what point vegetation is no longer connected to groundwater, but also look at the lag associated with that disconnection. So vegetation actually take time to reduce their canopy and drop leaves. So there could be a 3 to 4 month lag. So we'll be able to start unraveling those sorts of pieces of information, which can have significant impacts on managing water into the future and when is the best time to extract groundwater and not harm vegetation, for instance. The second PhD is currently actually being advertised, and we've focused that study to take more of an ecological and temporal approach to understanding how SAR can be used to monitor groundwater-dependent vegetation and connection with groundwater, with this concentrating on Nangara Mound, where there is this long-term continuous data set taken in the field, with an intent to apply the final method to the Murray-Darling Basin, where new data is also being collected over the next 3 years, and bringing this field collected data to help improve validation, understand temporal connection and disconnection of vegetation to groundwater. And all of this, of course, and I haven't talked about it too much, but all of this is related to understanding how we can help improve water management, inform when might be a good time or not a good time, or how to pump or not to pump. And there's this whole realm of groundwater extraction that increased knowledge provided by methods such as radar can start to inform and improve how we manage water into the future. And so on that note, I'm really happy to take some questions. And like I said, I won't concentrate on that technical detail, but we do have a journal paper that is available online, and the link is in this presentation.
Fantastic.
So, thank you.
Fantastic, Tanya. Thank you. It's been an absolutely fantastic presentation. Is that you in the picture there? I think
yeah, it is. So I'm a bit groundwater dependent as well.
Groundwater dependent person.
Yeah.
GDP? No. We have got questions coming up, so that's been fantastic. We'll get stuck into those right away. Thank you everyone for asking those questions. And let's start off with Jock Richardson. A great topic. In the GDE Atlas, there are a lot of potential GDE sites. I.e. not verified. Does this new method research rely on the Atlas for validation?
Yes, it does. So sorry, Trevor?
It's straightforward, simple.
Yes, it does. But we're moving beyond that with the PhD students and using field validation to also improve our area of validation and depth of validation.
No, thank you for that question, Jock. That's fantastic. One from Dr. Richard Evans. If the GDV, hi Rick, great to have you on board today. If the GDV are actually using unsaturated zone moisture, i.e. not groundwater, during a dry time, will SAR differentiate this?
Thanks, Rick. Great question. And that's exactly what we're hoping to have some focus on with the PhDs that are coming, especially the new one that will focus on Nangara Mound, where we have a lot of that ground data available to us to start unwinding that information. But again, this will require the multiple lines of evidence to help us determine if it's groundwater or stored soil.
Fabienne asks, Tanya, how large do you find you need the group of SAR readings, brackets, pixels, to have reliability of measurements?
Really good question, and probably not one that I'm able to comment on because I didn't do the SAR analysis, but send me an email and I'm more than happy to give you Pascal's email address and you can ask him.
Yeah, that's a great response, and thanks, Fabienne. What we'll do, Tanya, is we'll send you the Q&A questions in a report, so maybe that's
great.
Useful. Yep, no worries. Siamsil has asked, to what extent does the temporal and spatial resolution affect the modelling results?
At this point, again, that's something we're hoping to unravel with the PhD students. So what we've done is used a year of SAR data all brought together so that we've actually looked at an annual GDE layer at this stage. But my particular interest is definitely around the temporal connection and disconnection.
Right. Yep. No, that's great, Sam. So that's very good. Carissa has asked, does the GDE Atlas consider GDVs that may lie outside the identified GDE or riparian zone?
So I guess my short answer to that is we mentioned that in the journal paper that supports the GDE Atlas, and that journal paper is the one I've put a link to in this PowerPoint. And it's basically a caveat that no, because within the GDE Atlas, we had to stick with already available vegetation polygon mapping. Since then, some new mappings occurred, so, you know, and more finer scale. I hope that answered that question.
Fabian asked, how large do you need the group of SAR readings? She makes a comment, I think you see it in the chat line there, the review of monitored data and definition of temporal variability baseline could be great too. Just a
yeah,
comment.
I'm assuming that was a comment, and that's very much appreciated. Thank you.
Yeah, no, thanks, Fabian. We have got to the end of our open questions, and it's been a really good overview. It's not a book. If you want to go to the book, go to those references that my colleague Joel has been putting up. But we're drawing this webinar to a close. But before we do, I see Bill Senior. Thanks for coming on board and asking this question. I'm looking up Department of Environment, Queensland. Yeah, that's great. Bill says, really enjoyed the presentation, Tanya. Wondered if there is scope for verification of the SAR index versus some of our previous work we undertook together at sites used for the Queensland Floodplain Veg Project. We had a lot of multiple lines of evidence. Would be good to discuss this with you at some point. That's very good.
Thank you, Bill. It's actually also been on my mind whether or not that data was available. So it sounds like we can think about some sort of collaboration there, which would be wonderful.
That's fantastic. That's some of the nature of these webinars, to bring thoughts like this together, just synthesize them together, which you wouldn't normally necessarily just up and do. Well, look, we've come to the end of the questions, and it's been probing questions and good questions. Thank you, everyone. We're going to draw this to a close now. Just wanted to remind you that in the upcoming courses are listed there on the screen. Irrigation, water governance, water resources, managing groundwater, saline groundwater, water pollution. Not going to read them all. This happens every 2 months, so you'll have to go on the website and just take a look, or go into the YouTube channel or the Twitter address there at iSwarm. You can see. But look, in closing, as the webinar closes down, you'll see a short survey. Please do click on that and answer a few questions. That'll be really useful. And we're going to send a recording link to you so you can share it with your colleagues. Freely share that with your colleagues. That's fantastic. I thought maybe, Tanya, you may have one more closing statement you'd like to offer, you know, your closing blessing or closing good luck or whatever.
You know, in Australia particularly, GDEs are really important, but also your interest that you're showing is having a profound impact on other countries around the world. And I know that America especially is following the lead undertaken by many scientists in Australia. So I'm just representing one piece of the puzzle. It's a collective, you know, research that's going on. And there's so much more room for collaboration, as some of these questions have identified.
Absolutely.
So, you know, let's just keep this research on groundwater-dependent ecosystems and vegetation ongoing for the benefit of Australia, especially, and also for industry.
Well, yeah, what an important thing for industry. Yeah, that's right.
We want to support industry. We don't want to stop industry. Is my approach anyway.
Yeah, no, it's a great balanced approach. And I take away with me the key take-home message of multiple lines of evidence. I haven't come across the line, but obviously it's pretty clearly useful in this case. And it would be remiss of me to close it down, even though you've said your closing words, without bringing up this a comment from Rich, or actually it's a question from Rick Evans. Thank you so much for this question. With further research, Rick says, do you think the method will be able to give a quantitative indication of actual use?
Good question, Rick. Again, if we can bring in some other lines of evidence to support what we're showing with the canopy stability, and we are having advances in soil moisture remote sensing, we're having advances in evapotranspiration remote sensing. So I am hopeful. It might still be a little bit away, but that's definitely the trajectory we're heading, to start looking at this quantification of groundwater access.
Fantastic. What an absolutely great discussion. Really wide-ranging and well considered. Thanks so much, Tanya, and thank you everybody for joining us today. We'll call it quits there, and we look forward to you joining us again at a future webinar. Thanks so much, Tanya. Thank you, Joel, and everybody here that's helped us to get these webinars together.
And thank you everyone for attending.
Yeah, it's great news. Thank you, everyone. Bye for now.
Subscribe to this YouTube channel by clicking the subscription button. For future webinars and online short courses, please visit our website at australianwaterschool.com.au.